Welcome to the 39th lecture of combinatorics. In the last class, we had seen different sequences. So, this was the thing. So, we had some sequence, say something like H0, H1, H2, H3, H4 and so on. The first order different sequence, say written in the this, we say that is the zeroth row, and this is the zeroth order difference equation or different sequence. So, the sequence itself is called the zeroth order difference sequence, and here it is H1 minus H0, which we write as delta of H0. We will write delta of H1 for H2 minus H1 and delta of H2 for H3 minus H2 and so on, right. So, this will be delta H3. So, this sequence in the first line, first row is the first order difference sequence. Now, if I take the difference between delta of H1 and delta of H0, delta H1 minus delta H0 is delta square H0, and this is delta square H1, this is delta square H2, this means delta, so the gap here, right. Similarly, this is corresponds to the gap here, this corresponds to the gap here, this minus this, this minus this, this minus this, like that. This sequence is the second order. Like that, in the pth row we will have the pth order difference equation. So, this will be like here, somewhere here, pth order delta raised to p of H0 delta raised to p of H1 and so on, right. So, this table is called the difference table, and right, it is the difference table. This is what we saw in the last class. These concepts were introduced. Now, we will look at one property of the difference table when the underlying sequence H0, H1, H2 etc. Are given by the general term Hn, say it is a polynomial in pth degree, say np, say it is something like a1. So, suppose it is something like ap into n raised to p plus ap minus 1 into n raised to p minus 1 plus, like that until a0. So, if this general term can be represented using a polynomial, the pth degree polynomial in n, so where ap not equal to 0, so it is a pth degree polynomial. Then if you make the difference table, we will see that this being the zeroth row, the p plus 1th row onwards is fully 0, p plus 1th row will be 0, 0, 0, 0, 0, something like this. Until the pth row we will have some entries probably. So, but after that some non-zero entries, after that we will see only zeros, 0, 0, 0, 0. This we saw in the last class by taking an example where it was an n square 2n square plus 3n plus 1. So, when Hn was equal to 2n square plus, we saw that from the third row onwards, third row, when first row is called the zeroth row. So, so if you really count the rows, it is the fourth row, because if first row is the sequence itself, but but we call it zeroth row. So, first row, second row, third row onwards we were seeing all zeros for this thing, right. This is a general fact, that is what we were trying to prove. So, we will do it by induction. Suppose the degree of the polynomial is 0. So, degree of the polynomial, the p, it is a pth degree polynomial. So, degree p polynomial, suppose p equals 0, then it is a constant. Then the sequence itself will look like C, 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 C. Now, if you take the first order difference sequence, then we will get 0, 0, 0, 0, 0. That means these gaps are always 0, right? So, therefore, we see that this being the so this here being a 0 degree polynomial. So, this is the 0th line, this first line is the 0th line, the second line will be called the first line, first row, right. So, the p plus 1 equal to 1 here, the first row is 0, and then onwards we only get zeros, right, because the second second order difference equation is going to be also zeros, because anyway it is all zeros from starting from here. So, therefore, we infer that so when p equal to 0, the statement is true. Now, we will assume that up to p minus 1th degree polynomial, polynomials, it is true. That means, if the general Hn can be written as a p minus 1 degree polynomial, then we assume that the statement is true. That means, if you go to the pth row of the difference table, that will be 0, and from there onwards it will be 0 only. Now, let us consider the general term where the degree of the polynomial representing the general term is p, right. That means, Hn equal to ap into n raised to p plus a0, right. Now, let us look at the general term. Sorry, we will, by induction hypothesis, we know that for any p minus 1 degree polynomial or less, when the general term is a polynomial of degree p minus 1 or less in n, then the statement is true. That means, pth row onwards is 0. But now, for this case, we have to show that the p plus 1th row onwards is p plus 1th row onwards is right, is 0 is what we want to show, right. Now, if I find delta of Hn, what do we get? Means the first order difference sequence for this thing, if I evaluate for any n, right. So, it will look like this. So, ap into n plus 1 raised to, because this is what? This is Hn plus 1 minus Hn, right. So, this is ap into n plus 1 raised to p up to a0 minus ap into n raised to p a0. Sorry. Okay, this is what it is. Now, if we are looking for the coefficient of n raised to p in the expansion, right. So, after taking the difference, so what will you do? So, because from here onwards, none of the terms of n raised to p, because they are all p minus 1 degree onwards, here only one term has n raised to p. So, they only contribute to that. So, the coefficient of n raised to p in the resulting polynomial will be a will be coming from these two terms AP into n plus 1 raised to p and minus AP into n raised to p. But here if you take the binomial theorem, expand it, this will be n raised to p into p choose 1 into n raised to p minus 1 and so on. So finally 1, right. So minus AP into n raised to p. So here this n raised to p and this AP into n raised to p and this AP into n raised to p will cancel. We will end up getting p choose 1 n raised to p minus 1 plus finally 1, right. So we only have terms involving n raised to p minus 1 or less in this difference, right. So in other words, the coefficient of n raised to p will be 0 when I take this thing, right. So this delta of Hn is the first order difference sequence, that its general term is a polynomial in n of degree p minus 1 or less, right. So therefore we can, but now for such polynomials, this for we know that delta p of Hn is actually delta p minus 1 of delta Hn, right. So if you want to get the pth order difference sequence for Hn, so we only have to consider this sequence delta of Hn and take the p minus order p minus first order difference. In the difference table it is clear. So for this sequence where this corresponds to the 0th row of the difference table, we are looking for the pth row, and so in the difference table corresponding, if this is considered as the 0th row, then we are actually looking for the p minus row. These rows are same, so this is both are going to be equal, right. So therefore we can but then this we have already seen that is represented by a polynomial in n whose degree is p minus 1 or less. Now we can apply the induction hypothesis. So we are only thinking about the p minus 1th degree p minus 1th order difference. That means this will correspond to the pth row of the difference table for this one. So here, so okay, this is essentially the p plus 1th row, sorry. Yeah, so we actually this is correct. So what we want to show is that, so the p plus 1th row, namely delta p plus 1 of Hn is equal to 0 is what we want to show, right. We want to show that this is equal to 0, right. So this will be equal to delta p of Hn, right. Now this being a p minus 1 degree polynomial, this row, this delta p of this thing, this pth row here is going to be 0, that we already know. So therefore delta p plus 1 of Hn is also going to be 0, right. So from the difference table, what we have done is we considered the first sequence, right. We want to show that the p plus 1th row is going to be now 0. So the first row being considered 0th row, but to prove that we produced the first row, right. First row happens to be can be represented by the general term which is a polynomial in n of degree p minus 1 or less. Now this p plus 1th row for the first table, the other table, this table is going to be the pth row for this, right. So we know by induction hypothesis that because it is a polynomial of degree p minus 1 only, so this row is going to be 0. So the original this thing is also 0. So in this notation you have to write accordingly, right. The p plus 1th row correspond to the delta raised to p plus 1, right. So here, starting from here, when I tell delta of Hn, this correspond to this thing, delta p of Hn correspond to this row, right, the same row, okay. So therefore, yeah, it's an easy proof, just apply the induction, one has to carefully write the symbols, that's all. Then yeah, this is one property about the polynomials when the sequence is actually the general term of the sequence is actually a polynomial in n of degree p. So, then the p plus 1 through the difference table is going to be 0, and there on it is 0 only. Another property of the difference table is its linearity property. What is the linearity property of the difference table? This is very familiar. If you have seen this kind of properties before, it can be represented like this. Suppose Gn is a sequence and Fn is a sequence. That means Gn represents the general term of a sequence and Fn represents the general term of another sequence. Let C and D be constants, then delta P of C times Gn plus D times Fn is equal to C times delta P of Gn plus D times delta P of Fn, P greater than or equal to 0. Right. Now, if you want to carefully, suppose we have this Gn sequence. So, when you write the difference table, it will look like this. If you will write G0, G1, G2 like this, G3, something like this. So, this will be delta of G0, delta of G1 and delta of G2 and so on. This will be delta of square of G0. So, this will be the difference table corresponds to Gn. So, similarly, we will have one difference table for, we can write the reference for Fn, F0, F1, F2, F3, F4 and so on. This will be delta of F0, delta of F1, delta of F2 and so on. This will be delta square of F0, delta square of, this is the difference table corresponding to F1. Now, what we are saying is, what about adding this Gn and Fn together? That means every term here G0 will become F0 plus G0, the sum G0 plus F. So, if you add Gn plus Fn, what we get is, see, G0 plus F0, right, G1 plus F1, G2 plus F2 and so on. This will be the new sequence. Now, if you want to consider the second first row of this thing, that difference table, the new difference table for Fn plus Gn, right. So, we have to minus this thing. This is G1 minus G0, right, G1 minus G0 plus F1 minus F0, which is nothing but G1 minus G0 is actually delta G0 and this is actually delta F1. So, F0. So, this is delta G0 plus delta F0, right. Similarly, this will be delta. So, if I take the minus here, you can easily see that this G2 minus G1, which is delta G1, this is F2 minus F1, that is delta F1. So, this is delta G1 plus delta F1, right. So, delta of Fn plus Gn is clearly delta of Fn plus delta of Gn, right. This is one thing which you can easily observe. Similarly, we can easily see that if you have a sequence, say G0, G1, G2, etc., and I multiply with the constant, that means C, this is the new sequence, suppose, right. So, this is the new sequence, C times G3, C times G4 and so on. Now, if you take the difference thing, so if I consider C G1 minus C, this is delta of G0, that is C into G1 minus G0 only will get, which is actually C times delta of G0. Similarly, when I take CG, so here the gap, C into delta of G1, this will be C into delta of G2 and so on, right. When you take the difference here, this is C into delta square of G0, this is C into delta square of G1 and so on. This is C into delta cube of G0 and so on, right, which you can easily see that from which you can easily see that if Gn is a sequence and Cgn is the new sequence, right. So, then delta of Cgn is going to be C times delta of Gn, and actually we can extend it to delta of P of C times Gn is equal to C times delta P of Gn, right. This second statements can easily be proved by induction, because we proved it for the p equal to 1 case. Now, if you want to prove it for general p, what we see is that delta raised to p of gn, c times gn, is actually, we apply this as delta into delta of delta p minus 1 of c times gn, right. This is what it is. So, now if you apply this thing on this, right, we know already, we have proved already for the p equal to 1 case. This is essentially sorry, first we apply here, because by induction we know that this we can write, this portion we can write as c times delta p minus 1 of gn, right. So, now we can apply this thing, we already, because for p equal to 1 we have already proved. So, that is c into delta of delta p minus 1 of gn. So, which is essentially c times delta p of gn. This is the situation, right. So, now similarly we could have proved delta p of gn plus fn is equal to delta p of gn plus delta p of fn, right. So, this also follows by induction, the same kind of argument, right. Now, from both of this thing, what we can infer is delta p of c times gn plus d times fn, where d and c are some constants. This is what, first we apply the first rule. So, this will be delta p of c times gn plus delta p of d times fn, this way we can write, and then we can apply the second rule, namely this is equal to c times delta p of gn plus d times delta p of fn, right. This is what it is, this is the linearity property, right. So, which essentially means that if you have these different tables, right, this table and this table, when you create, if you want to create the difference table for gn plus fn, we can simply add, for instance, term by term we can add, g0 plus f0 is added here. So, the first row is obvious because that is by definition, but the second row also we can add. So, this and this will add and will stay just below the, so in this gap, right, the first gap. So, similarly, or other words, the first order difference sequence also is a sum of this first order difference sequence and this difference. Similarly, the second order difference sequence also can be added. So, that is what we are saying. Actually, if you are similarly, if you are multiplying the difference table, the first row, the difference table by a constant, every term is multiplied, then all the coming rows also will get that multiplier, and then when you want to add them together, naturally we can add the tables. That is what, if you want to visualize using the tables, this is what it says, right. It is a very simple property, but if you just think for some time, you get it very clearly. Now this is the linearity property of that. Now, another interesting property of this difference table is that this difference table can be completely written down if you know the starting terms in each row. We know very well that if the sequence itself is given, the difference table can be, for instance, if the first row of the 0th row of the difference table is known, then the difference table can be completely written down, right, completely written down, as long as, yeah. So, we are ready to write. If there are infinite rows, then of course we can. So, it is completely determined anyway, right. So, but that is because that is the way we are defining, because once the first sequence is given, then the first order different sequence is written and the second order different sequence is written, and so on. Now, we are telling we can also do create this difference table if we had known these things, delta of this one and delta of h0, which is essentially the first term in the second, the first row term in the first row. This is the 0th row, this is the 0th row, this being the first row, this first term, and here delta square of h0, this is delta square of delta cube of h0. If these terms are known, then also we can complete this table. Why? So I am assuming that I do not know anything here, right? I know only this, this and so on. How can I write? So first I write this is what I want, because I know that this term is this h1 minus h0, right? So this h0 I know, right? So clearly I can create h1, right? Delta h0 and delta h0 plus h0 will create h1, right? So that means this can be created by adding, so this is h0, adding these two things, right? I can, if I add these two things, I will get this, right? So this will be h1, because h1 minus h0 is this, so this plus this is this. Similarly, this here, this number here can be created by adding this and this, because this minus this number minus this is this, so this plus this will be this, right? So this will be what? Delta square of h0 plus delta h0 will be this, because we know both of these things. I can write it down. Similarly, I can write this number by adding this and this, right? So like that I can create this entire second diagonal, this being the 0th diagonal. The first diagonal we can create, this is the leftmost diagonal. So this left edge of the table, you can see this is first, and after that the next diagonal can be created, and then next diagonal can be created. How? We will add this and this, and we get this thing, right? So we will add, why is it so? Because this number is produced by this minus this, right? This number minus this was this. So therefore, to get this number, we just have to add this and this. Similarly, this number is produced by this number minus this number is this. So in this row, right? So therefore, to get this thing, you just have to add this. So once you know this diagonals, you can produce the next diagonal and so on, right? So it's very clear that if you know this left edge completely, then we can create the rest of the difference table. To summarize, what I am telling is you can your difference table is completely determined either by your first 0th row, which is essentially h0, h1, h2 sequence itself, which is not at all surprising, because that is the way we define the difference table. But what is interesting is it can also be completely generated if somebody gives you only this left edge or 0th diagonal of the difference table, namely these numbers h0, delta h0, delta square h0, delta cube h0 and so on. This numbers alone are given, then we can write down these numbers, then we can write down these numbers, and then we can write down these numbers and so on. Completely we can generate the entire table from this thing. So the difference table is determined either by this line or this line, right? The rest automatically follows. So then what is the advantage of having this thing? The advantage is that this line can be, say, for some cases, if this first 0th row is actually an infinite sequence, in the sense that there are an infinite number of non-zero entries there, right? It may so happen that in this diagonal we have only a finite number of non-zero entries. That may make our life easier, and you may wonder in what situation it happens. We have already mentioned one situation which is important enough to motivate this study. So namely, when Hn is of the form, see, ap n raised to p plus ap minus 1 n raised to p minus 1 plus a0. That means Hn has the form of a polynomial in n, right? of degree p say, then we have seen that if you look at this sequence of numbers, namely h0, delta h0, delta square h1 h0, delta cube h0, this will go up to delta p h0, but delta p plus 1 h0 onwards we are going to have zeros. This is going to be 0. Why? Because I know the p plus 1th row is going to be 0. That is what we proved in the previous theorem, right. We have shown that if the general term is given by a polynomial in n of degree p, then the p plus 1th row onwards is going to be 0, p plus 1th row, p plus 2th row and so on. And in particular the first term of that rows, namely delta p plus 1 of h0, delta p plus 2 of h0, delta p plus 3 of h0, all of them will be 0. So, we will have non-zero values possibly up to here, not beyond that, right. So, this is, while if you write down, if you try the 0th row, it may go on and on, because there may be several non-zero entries, infinite number of non-zero entries in the first row. So, that way we cannot concisely represent this table, but on the other hand, if you look at the left edge, on the other hand, this 0th diagonal, we know that starting from h0 we will have to consider only delta p of h0, namely p plus 1 numbers along the 0th diagonal, right. This will completely determine the difference table. This is the advantage of understanding that. So, this full difference table can be represented either by the 0th row or by the 0th diagonal. So, now that we have this understanding, let us look how we can make use of this thing, right. The good thing is, so the 0th diagonal may look like this, 0, right, C0, C1, C2, say some CP, and beyond that it may be all zeros, right. Suppose it is a polynomial, in the case of polynomials, right. Say for instance, if for my general term Hn was some polynomial of this form, that means nth degree polynomial, then these numbers 0, C0, C1, C2, Cp, these numbers may be non-zero, but beyond that all of them will be 0, right. But now suppose if this one was 1 and all the others were zeros, right, if all the others were zeros, let us say we can get, so let us call it this sequence as EP, right. EP means this sequence is EP, say EP, right, EP1, EP2. So, which I mean, what I mean is in the pth row, this being the 0th row, this being the first row, this being the second row, this is the pth row. Pth row we have 1, all other places we have zeros, all other places in the 0th diagonal, here. We are not bothered about what is going to be in these places as of now, right. So, then this sequence, which we may write it as EP0, EP1, EP2, right, this sequence, suppose if I can figure out, right, the general term being EPN, right, then you can easily see that the table which is generated by C0, C1, C2, Cp in the main diagonal, this kind of a table, right, this table can actually be represented. So, this table will be giving a, say for instance, some Fn, right, some general term will be coming here for this thing if I work out this thing, but the general term can be written as Fn equal to C0 into E0n plus C1 into E1n plus Cn Cp into EPN. Above that we do not have the CPs are all zeros, right. So, this can be written like this. Why is it so? Because of the linearity property of this thing, right, because this term is actually C0 times 1, right, and if you could have decomposed these tables like C0 1 1 sorry this 0 0 0 0 a table corresponding to this this 0th diagonal, and C1, so another table corresponding to 0 C1 0 0 0 and so on, and another table corresponding to 0 0 C2 0 0 and so on, right. And if you add these things together, this row will be C0 C1 C2 C3 up to Cp, right. And this particular table C0 itself could have been produced by multiplying the by C0 the table which is produced by 1 0 0 0 0 1 0 0 and so on, right. This table can be produced by multiplying the table produced by this left diagonal 0 1 0 0 0. So, therefore, overall, so if you want to get the general term corresponding to the difference table where the 0th diagonal of the difference table is C0 C1 C2 etc., what we do is we create the table corresponding to the 0th diagonal of this form 1 0 0 and then multiply that table by C0. Then we produce the table which corresponds to the 0th diagonal of this form, and then multiply by C1 and then add it to the previous one, and then we produce the table corresponding to 0 0 1 0 0 and then multiply by C2 and add it to the previous and so on, right. Then up to we have to do it p plus 1 times, by once for C0 once for this, one for this, one for this, one for, and that will create the general term for this, right. So, but for this to be effective, we should have a very concise and neat formula for the general term corresponding to the for the sequence corresponding to the difference table produced by this kind of a 0th diagonal, right, this kind of a 0th diagonal. So, here it is the pth position. So, here pth row we have 1, right, this is 0th row, this first row, second row, this pth row is having 1, right. Now, if you want to reproduce, I mean the general term here, that means the first row, what will be Hn here, right. Now, so you know that how will this second sorry the first diagonal look like. This is the 0th diagonal, and the first diagonal will look like, definitely this and this should be added to get this, this and this should be added to get this, and it will look like this, right. Yeah, and then this, sorry, here we will get 0 and 1, this will be 1, right. Now, here also it will be 1. So, but let us discard for the time being. From here onwards it will be all 0, we know that. So, okay, this will be all 0 because 0 plus this one, but here this row we will have something, but for the time being let's not worry about this portion. Similarly, if I create this thing, this will be 0, this will be again 0, this will be again 0, and this will be 1, right, and here it will be 0 and then 0 and there will be a 1, so on, right. So, we will be getting something like this upward, right. So, 0 1 and then we have a 1 and then we have a 1, like this we will be going upward. So, if you have P here, then same thing we will get right here. So, like this here we will have a sequence of ones going upward like these zeros the same way, right. So, here we have this is the pth one, right. So, here we have up to p minus 1, this is 0th, this corresponds to h0, right, this corresponds to h1, this will be hp minus 1, right. So, and this will be hp will be always hp will be 1, Now looking at the structure of this thing, so let's, because from till p in the pth row we have a 1, then beyond that we are getting zeros. So we are not sure whether yeah, so we can also, examining this thing, we can also get that all these zeros are coming here, right, because that's the way this and this will add to this and this will add to this and will. So it's a very reasonable guess to think that the corresponding general term will be a polynomial in P. So we will assume so. So if it's a polynomial in P, then can we find that polynomial? It may look like yeah, can we find that polynomial? But one good thing is that we know that when we substitute n equal to 0, that polynomial evaluates to 0. When we substitute n equal to 1, that polynomial evaluates to 1, and when I substitute n equal to 2, that polynomial evaluates to 0, and so on. So here, because this first row is something like 0 0 0 0 0, and suddenly the pth term is becoming 1, right. So therefore we can see that we have h0 is equal to 0, right, h1 equal to 0, say like that hp minus 1 is also equal to 0, and we have hp equal to 1. This is what we see, right. So what does it mean? So we know that if it is a polynomial in n, then the roots are 0, 1, p minus 1. We got all the p roots of it. So it will look like 1 n minus 0, that polynomial look like n minus 0 into n minus 1 into n minus p plus 1, right, n minus p minus n minus p plus 1, and some constant. This will be that polynomial. P of n will look like this, right, some constant times n minus 0 into n minus 1 into n minus. So this is like c into n minus 1 into n minus 2 into n minus p plus 1. This is the way it will look like. Now but how will, this is p of n, but how will I determine the value of c then? So to do that, we have one more value available, this hp equal to 1. That means when you substitute n equal to p, so this I can use a different symbol for this. So let us say h of n, so h of n, no, sorry, f of n. For that polynomial, let me use, yeah, this kind of a p, right, p of x, right, because I am just confusing with this p. Now I will just substitute n equal to p, then this will look like c into p minus 1 up to p minus p plus 1 up to 1. That means our constants, but value of this thing is already known, right. So right, or I can always use the h itself for the polynomial. Only thing is that, let me use the capital H for the, to denote that it is a polynomial, right, h of n, right, h of n. So so n is to be considered as a variable here in this polynomial. So this h0, h1 etc. are the terms of the sequence, small one. I just use capital letters to denote that we are talking about a polynomial, right. So let me see, this is h of p. So h of p actually will evaluate to hp, right, which is actually 1, right. This is equal to c into, this is what, p factorial. So the c is equal to 1 by p factorial, right. So what is our answer? So we can substitute this 1 by p factorial here. So we will get h of n is equal to 1 by p factorial into n into n minus 1 into, so n minus p plus 1. This is very familiar to us. This is actually n choose p, right. So n choose p, which also can be written as n p falling factorial by p factorial, right. So this is the n falling factorial, and falling starting from n into n minus 1 into n minus p plus 1, right. So this way we can write, or just write n choose p, right. So the polynomial corresponding to the sequence which corresponds to the difference table whose 0th diagonal is 0 0 0 up to p. So up to the pth position we have 1 and then 0 0 0. So 0 0 0 and the pth position we have 1 and then 0 0 0 0 will be n choose p, right. So n choose p, n falling factorial p, n is taken as a variable here, and falling factorial p divided by p factorial. This is what. Now we know that if we are considering the difference table for C0, C1, C2, this suppose 0 diagonal look like this Cp, and then below that 0 0 0, and then if you create this first 0th row, and then what will be Hn, what will be the general term here, right. We know that this will correspond to by the linearity property of these difference tables, right. So we can multiply the C0 into E0n, which is, we know already this n choose 0, right. C0 into n choose 0 plus C1 into this C1 into E1n, we know this one is C1 into what, n choose 1, and up to p we can do Cp into n choose p, right. Because if you just had one in this position and everywhere else it was 0, then that will correspond to n choose p, p being the row number where the one has occurred, right. So if one had occurred in the 0th row, we will get this one first row, the first place of the first row, I mean. So then it will be this, and the first place of the, and the multipliers are definitely C0, C1 up to Cp, and when you add up we will get like this, right. So if the difference table look like C0, C1, C2 up to Cp, and then 0 0 0 etc. So we see that our Hn, the general term corresponding to the sequence coming from this difference table, is actually sigma I equal to 0 to p Ci n choose I, right. So this will be the general term for such a sequence. So that is what we are getting. So now yeah, so the only one thing we have forgotten to discuss is that, right, we have figured out a polynomial which will corresponds to this general, this kind of a 0th diagonal, and then right. So yeah, it is easy to verify that this polynomial and choose p actually corresponds to this 0th table. We guessed it first, but then we saw that up to here it is satisfying. So up to the p plus, so 0th term, first term, up to pth term it is satisfying. Now we can see that this thing, this portion of this difference table is following from that. If it is satisfying this much, and up to here it is satisfied, right. So and then we know it is a, this n choose p is a polynomial of degree, so sorry, up to here. So this is what I mean is 0 0 0 1, right. This is the pth position. So this portion of the table, so where this is 0 to p terms here, so see h0, h1, h2, hp, and this is up to 0 1 2 up to pth row, right. This much anyway will follow. If you can definitely see that this is 0 0 0 1, then we will get 0 0 0 0 1 and 0 0 1, and this portion of the table will come, and from here onwards the therefore up to here it is actually giving the 0th diagonal as we want it, and since n choose p is a polynomial in degree p, p plus 1th row onwards we should have 0 0 onwards. So, this will also satisfy the remaining things. That is why we just have to verify that after getting this answer n choose p, that it actually corresponds to the table, corresponds to a table where the 0th diagonal is looking like 0 0 0 0 and a 1 in the pth row, and then 0 0 0, right. And you know, once this is matching, the 0th diagonal is matching, the entire table will match, right. So, we do not have to worry more than that. And then once that is true, then it was only the linearity property we used, and then we just can multiply the corresponding terms with C0, C1, C2, etc., and then we end up with this formula for the general term. Now, we can simplify a little bit. Suppose yeah, so this can be written as Hn equal to, right, sigma I equal to 0 to p Ci, assuming that the diagonal, so the main diagonal look like C0, C1, C2, Cp, and then 0 0 0, right. The first 0 diagonal look like this, Cp into this is n choose I, right. But this n choose I, as we have mentioned, is in I falling factorial divided by I factorial. So, now this can be written as sigma I equal to 0 to p Ci by I factorial into n I falling factorial, right. So, this is this polynomial can be represented by this. See, we can say h of n. This h of n can be represented by, so actually is nth general term. So, general term for the n. So, if you want to write it as polynomial, we can write h of n. So, can be represented like this. Now, we will just notice that if you are familiar with linear algebra, it is not very surprising, because if you are talking about a polynomial, say h of n, which is of degree p, right. So, definitely if you consider the vector space of polynomials of degree p, then you know 1 x square x raised to p form a basis for this thing, these polynomials. Also, if you want to use n1 n square n raised to p form a basis for this thing. Similarly, it is not difficult to show that n choose 0, n choose 1, n choose 2, n choose p, which are also polynomials. This in 0, this is a constant term, this being a degree 1 polynomial of degree 2 here, this is degree p polynomial. This also form a basis for h of n, and naturally you can simplify this thing and say that n0 factorial, which is a constant, n1 falling factorial, n2 falling factorial, n falling factorial. I hope you recall the definition of falling factorials. When I say n p falling factorial, I mean n minus 1, n minus 2 up to n minus p plus 1. This is what this thing. This is also a basis for this vector space, and therefore it is not surprising that any polynomial of degree p can be represented as some constant into this plus some constant into this plus some constant into this plus some constant into this, right. It's not at all surprising. So, but again we want go to linear algebra much. So, the presentation use of course we could have told like this as unique coefficients are there, but the previous presentation using difference table gives a little insight into what kind of numbers these things are, and also it is not about only about existence we are talking about, we are seeing actually the numbers which are appearing here, right. So, okay, fine. So, then what we have now told is any polynomial can be represented like this. So, as the coefficients of following factorials. So, in the basis of using the following factorials we can represent any polynomial. Now, what we are especially interested in is the simple polynomials like n raised to k, n raised to p, let us say. So, we want to represent n raised to p as I equal to 0 to p, right. Yeah, we need only up to p for this thing. So, where this is so we will use Cp0 because we are talking about n raised to p, Cp0 rather than C0, C1 etc. we will call C of p comma 0, p of p comma 1 because we are talking about the coefficient of coefficients when we want to represent n raised to p, right. So, into n choose p, right. So, this numbers are special. So, because we are studying this n raised to p. So, we can represent n raised to 0, n raised to 1, n raised to 2 and so on. So, in general this is true because this is true from the previous discussion because n raised to p is just a polynomial in degree p. So, whose degree is p, therefore, this is also possible. This coefficients we have changed just to note that we are actually representing n raised to p, that is why C of p is coming, and then this will go from Cpi I equal to 0 to p, it will go from I equal to 0 to p. So, it will look like n raised to p equal to Cp0 into n choose 0 plus Cp1 into n choose 1 and so on till Cpp into n choose p. Now, so this also can be, as we have already mentioned, this also can be represented Cp0 by 0 factorial into n 0 following factorial. So, it is just one constant, and then Cp1 by 1 factorial into n 1 following factorial and so on, Cpp by p factorial into n p following factorial. These numbers Cpk by k following factorial appearing here will be the Stirling numbers Spk. So, we will show that this is the same Stirling numbers we have defined, Stirling numbers of the second kind that we have defined before using a combinatorial definition. By what our strategy is to show that this Spk, these numbers actually satisfy the same recurrence relation and initial conditions as the previous the Stirling numbers of the second kind which we defined using the combinatorial interpretation, right. So, that is what we will do in the next class.